Hello and welcome to Chapter 8, Implementing Virtual Private Networks. So tonight we are going to discuss how VPN works and how to configure a remote access VPN and a site-to-site VPN. So let's get started. So what is a VPN? A VPN is when you have either a remote host or a remote site wants to connect to the main site, for example, or two different sites that are in different geographic area, and they want to use the public internet to send their data. Since the public internet is unsecured and unregulated, so what you need to find a way where you can pass the data in a secured manner. So what you do is you create a tunnel and you send your data inside that tunnel. What that means is creating a tunnel is you take your packet and you are re-encapsulating it with another packet. So your original packet is inside another packet. That's the tunneling. And then you go inside where your packet is, inside the tunnel, and you encrypt it. So a secured VPN is a secured tunnel with an encrypted data. So because you can use the internet, it's the least expensive way to connect two different sites. It's very secured, scalable. You can almost connect any site and anywhere at any time. You can have multiple sites connect to this main site, and it's compatible with almost anything. We're going to use IP security, so you can have mobile users, sites, and it's like I said, it's scalable. So please write that down. VPN benefits and what they are: the cost savings, the security, the scalability, and the compatibility. All right. There are, by the way, there's layer 2 and layer 3 VPN. You can set up VPNs in both ways. At layer 2, for example, MPLS, the multi-protocol switching protocol, a layer 3 protocol, allows you to do, it's a type of a VPN, but we're going to be discussing specifically layer 3 IP security VPNs. So we'll take that step by step. Okay, so the remote access VPNs are when you have a client on their computer where they can actually initiate a VPN connection to the terminating site. Anytime you do an HTTPS, you are actually initiating a VPN connection to the server that you are trying to connect to. Site-to-site VPN, you are at a remote site where you send your data to the router and then the router will set you up. You don't even know that you are connecting to a VPN. You'll be accessing resources from another site as if those resources were, next door to you, as if it was local. Right? So that virtual private network allows that connection as long as you have pretty good bandwidth and you're guaranteed that connection security is not an issue. All right, so you have those two types: the remote access where the client actually initiates the connection, and with the VPN you have your router is the one that takes care of that. We're going to be concentrating and we're going to take a look at how to set up a site-to-site VPN, because this is really pretty straightforward. You don't even need any software on here when you are doing a client, a remote access. The browser itself does all of that for you. All right, so we're going to be concentrating on setting up a site-to-site VPN. Okay, so let's take a look at the IP security technology. IP security is a suite of protocol that allows you to get to choose on how to set up your VPN. For example, if you chose that you want a tunneling or a VPN that only does authentication and just authenticate the header, you do not want the encryption, the data, the payload to be encrypted. So if you chose that as your IPsec protocol, then you get the choices. Remember, we're not doing any confidentiality, no encryption of the actual data that's inside the tunnel. So the data, if you chose AH, You are not encrypting the payload. You just want to make sure that the data has integrity. You authenticate the user, and we'll use the Diffie-Hellman to pass keys to each other. If you chose that you want to encrypt the payload, you choose ESP, then you have one of those different choices, DES, triple DES, AES, or the seal, to encrypt your payload. And you can also check for the integrity, the authentication, and you can use any of these Diffie-Hellmans to exchange symmetric keys to each other. You could choose both AH and ESP, you can authenticate the header, and typically that's what's usually done with a secured VPN. ESP, the encrypting of the payload, and authenticating the header. So that's typically what's done with a site-to-site secured VPN. All right, so when we talk about confidentiality, as you already know, you want to encrypt the data. When you send your data is encrypted with a key, and you transmit that encrypted data. If there is an unauthorized user, the man in the middle, he won't be able to decipher the data. It's either because he doesn't have the key, and if he has the key, it's most likely, then we're in trouble, of course, if he has the key, the same key as the other guy. And it could be, by the way, a protocol analyzer, the man in the middle guy, any unauthorized users that's eavesdropping on the data that's traversing the network, and they won't be able to decipher what it is. And once the data received, this guy will be able to decipher the data using the same key. Remember, we want to use symmetric key because the idea behind the symmetric key, it's much, much faster than use asymmetric. That means both. This guy, what's his name, Gail and Jeremy will have the same key. That's symmetric, right? If it's asymmetric, Gail will have the private, encrypts with the private, and Jeremy will decrypt with the public key. Okay, so the encryption algorithms that are offered by the IPsec is the DES, the triple DES, the data encryption standard, the triple DES, the AES, and the seal. And depending on which one you choose, the most widely used is the AES for encrypting the payload, right? All right, so the hash algorithm is the ones that checks for the integrity of the data. Remember, checking the integrity, meaning you want to make sure that the data that's being transmitted has not been tampered with, not altered, right? So when your data goes through a hash, a number comes out, and you stamp that on the data, and when you send it out, you hash the same data and make sure that the hash comes out the same as the one that's been stamped. If it's the same, that means the data has not been altered. So for example, in this example, you're sending a check for $100. And when you hash it, you get this number out. You stamp it on the check and you send the check out. For example, on the way, they changed the 100 to 1,000. So when you received it with the 1,000, the data been altered. When you run the hash, you got a different number. It's not the same that's been stamped. So therefore, it's no good. You know that the check has been forged. Somebody changed something in it. It doesn't matter what it is. You just do not accept it, right? If the hash came out the same, that means everything that was on the original check is the same, was received. Authentication, you want to make sure that you can authenticate the user. Peer-to-peer authentication. You give me your it's a pre-shared key we can use. Everybody has the same key, so I'll encrypt, send out the data, and you can decrypt with the same key and make sure that the original is the one. Make sure that the one that does not have the the problem with pre-shared key is if somebody grabs the key, then they can alter the data, or they can decipher what the data that's being transmitted. Who is the sender? Who is the receiver? But if you use the RSA, that means you are using a public key and a private key. So this is more secured for authentication purposes than the pre-shared key. But pre-shared key is much, much quicker. Okay, so RSA, what it does is you use, again, a private key and a public key to, excuse me, to authenticate the users. Okay, it takes a little bit longer, but it's a lot more secure than pre-shared keys. Okay, SSH does that first, if you remember when we're doing SSH. When it comes to Diffie-Hellmans, there are different choices. You have Diffie-Hellman 1, 2, 5, and there's a whole bunch of Diffie-Hellmans. The higher the number, the more secure it is when you are exchanging pre-shared key. Okay, so there's a mathematical equation that you can use where you and the receiver on the other end, the sender and the receiver, will have the same pre-shared key exchanged without anybody in between really knowing what that number is. Actually, you can using mathematical equations, the key that comes up, it's kind of random, but it's very easy, and I'll show you how to do that in class if I did not already. How Diffie-Hellman actually use prime numbers, that you come up with any prime numbers, you pass them to each other, and you use something with the mod, the remainder, and by exchanging that and playing with the mod and a little bit of the exponent, we'll explain all that. You'll come up at the end um, with the same key. And that's how it's done. Diffie-Hellman, that's mainly what it's used for. So when you are setting up a VPN, you use Diffie-Hellman to give the symmetric key to both sides. Once Diffie-Hellman does his job and he makes and each side has the same key, his job is over. He doesn't do anything else for the rest of the VPN session. He's only there to exchange keys. All right, so let's take a look at the IP security protocols. There is the AH, like we said, only authenticates the header. ESP encrypts the payload. ESP and AH does both, authenticates the header and encrypts the data, right? So if you're going to do AH, again, here's your choices. There's no encryption in here, encryption the payload. Only you want to make sure that R1 is R1 and R2 when they're talking to each other. You're authenticating the header and you're making sure that the data that's being passed does not get tampered with. That's the integrity. The authentication is, you got the choices with PSK and RSK. And Diffie-Hellman is the one that's going to exchange the keys for both of you before you exchange the pre-shared key. For example, if you chose Diffie-Hellman 2, you'll choose Diffie-Hellman 2 to generate the key exchange, the pre-shared key, the same key for both. And then we'll use these keys and the depending on what type of hashing you want to hash the data. Okay, that's the AH. All right, and when it comes to ESP will not only does the data that's inside the tunnel is encrypted, and there's the encryption choices. You can use the DES, the triple DES, the AES, or the seal. And of course, you can also double check the integrity of the data. Diffie-Hellman will exchange keys with appreciate keys for the confidential, for the encryption. And then you can do both. When you're encrypting the ESPN, by the way, you are encrypting the actual IP packet plus the IP header. And then you attach in the ASP trailer and you encrypt in all of that, and then you're authenticating everything right here. So that's the best way to do it. And then you're just adding a new header. That's the tunneling. So when you're passing the VPN, we'll see the new header, and we'll have to decrypt everything when it gets it on the other side. There are two different ways or two different modes that you can use ESP and AH. You can use them in the transport mode or the tunneling mode. So in the transport mode, you are only encrypting anything from the transport layer and above. So the packet and the IP header does not encrypt it. So when you pass anything in the transport mode, the IP header will be seen, the IP addresses, in other words. So this is really used, the transport mode, if you are inside a LAN. So you want to encrypt the data that's inside the LAN, and you want your routers inside your building, inside your secured network, to be able to see the IP addresses, but you still want the data to be encrypted. Uh, the tunneling mode is when you want to go outside your LAN over the internet. You want to encrypt everything, including the IP address on the packet. Everything should be hidden. That's the tunneling mode. You go through the tunnel, the VPN. So when you're setting up a VPN, you're using ESP and AH in the tunnel mode. Okay, so that's that in the tunneling mode. Okay, now let's look at the IKE, the Internet Key Exchange. So you have a local peer and a remote peer. When you want to set up uh, a VPN, the Internet Key Exchange has to exchange and pass information to both peers and keys to set up the VPN itself. So whatever you do on one side, the other side has to agree to exactly the same protocol. So if you're going, for example, to choose AES as your encryption method to encrypt the payload, the other side has to do this exactly the same thing, because you can't encrypt in AES and then the other side encrypts in triple DES or decrypt. Then you won't be able to, they'll be able to do two different things. So whatever you do on one side has to be done on the other side. IKE is the one that negotiates both of these. Negotiates means, here, the local peer will send and tell him, listen, this is what I'm going to do. I'm going to use ESP and AH as my IPsec protocol, and here are my choices. So IKE sends that information to the remote, and then the remote says, okay, I agree. He sends that information back, and if you both agree, then everything is okay. Then you start passing data. And we'll talk about how to set that up. So IKE is the one that passes information back and forth between the local and the remote peers to allow them to set up the VPN. All right, so there are two phases. Phase 1 and phase 2 negotiation, the key negotiation. Okay, phase 1, negotiate the AIESEC policy to create a tunnel. So the first thing you want to do, there's two phases. So remember that. Please write those down so at least you'll remember. It's not that difficult. Phase 1 is you negotiate, you set up the tunnel. So you create policies when you want to set up the tunnel. Policy 1, 2, 3, 4, how many policies you want. What a policy is, each policy you can say, all right, here are my choices of how I want to set up the tunnel. Policy 2, you'll have different choices. Policy 3, and so on. Policy 1 will be the primary one that has the highest priority. Then you policy 2, policy 3, and policy 4. Right? So usually you create one policy. This guy has policy 10, for example, has the following protocols, and this guy has policy 15. So you send him policy 10, and he says you policy 15, and you say, okay, let me see policy 15. It agrees with my policy 10, then we're all good to go. The tunnel is set up. So AIESEC negotiate the policies to create the tunnel. Now, if policy 10 does not agree, so you may pick up a different, so you look up for a policy on your end that agrees with this policy 10. If not, then you will never be, if you don't have any policy that has these protocols, you will not be able to set up your tunnel. That means probably you don't have one of these protocols available for you. All right, but typically you set these up. So you create one policy, you go to the other end, on the other end, and you create another policy of exactly the same protocols, and your tunnel is set. Simple as that. Very easy commands to do. So phase 1 is you negotiate AIESEC policies to create the tunnel, right? And once you do that, once you pass days, then the Diffie-Hellman will exchange the keys, and we'll make sure that the keys are all good, and then we'll authenticate the users. Make sure that the users are to say who they are. Is it you? Are you R1? Are you R2? And so on. And once that's done, then you write, and then phase 2, you negotiate the actual data that's going to the payload itself. So let's go. How are we going to, remember this word, transform the data, encrypt the payload. How are we going to transform it, encrypt it, and then send it out? So there has to be another set of protocol on how the actual data is going to be encrypted inside the tunnel. That's phase two. So that's negotiating the association between both, the encrypting. That's phase two. All right, so now let's take a look at actually implementing the site-to-site VPN. So let's take it step by step. I want you to write these steps down. Okay, so phase one, step number one, the negotiation between A and B. Step two, R2 is going to negotiate. So step one, A sends out the interesting data. Interesting data is, for example, is data that's going to be passed to this network. So that's interesting. I look at, for example, I have to create, you would think you had to create an access list that says if the following data is coming from 10, 0, 1 network and going to 192.168 one network, do we have to trigger a VPN? If you are going to the internet somewhere else, that's not interesting data. That's not going to trigger a VPN. So interesting data is when the router looks at the where you're going, and if it's according to the access list that's going to trigger a VPN, then you go to step two. So the interesting data has triggered a VPN. And then step two says, okay, let's set up the tunnel, do a phase one, and then let's talk about in step three, then we're going to negotiate how we are going to encrypt the data inside that tunnel, right? Those are the three steps. And then step number four, you actually exchange the actual data, you're passing data within the tunnel. And then when you're all done, the tunnel is terminated. It's not being used. All right, so those are the 5 steps and what happens. So here is the different topologies you need to know. When you are setting it up, by the way, you need to know the original, the LAN network and the destination, and you need to know these IP addresses on the serial ports that communicates. That's pretty much it, really. And the rest is a matter of choosing the correct protocols when you are setting up your LAN. You're setting up your VPN, sorry. Excuse me. So the configuration tasks. So please write those down. So for example, this is just an example. So you want to encrypt all the data, for example, with AES 256 and SHA. That's going to be your encryption. And your authentication is going to be a pre-shared key. You're going to use group 24, Diffie-Hellman, to exchange the keys. You want those keys that are being passed to have a lifetime of 1 hour. After 1 hour, you're going to ask Diffie-Hellman to terminate those keys and exchange new keys, right? And then you're going to, you want the tunnel use ESP with 15-minute lifetime, with a 15-minute lifetime. So the configuration task, you're going to configure phase one, phase two, configure the crypto map for the IP policies, and then apply the policy, and then verify that the tunnel is working fine. So that's your job. So how we're going to do this. These are given to you. This is the requirement, and this is your configuration tasks. So your job is to go through those 5 steps on the configuration tasks. All right, so you create for the interesting data, for the first step is to create an access list. Okay, so the first access list you are going to create is to permit the traffic for IPsec negotiation, to allow the key exchange keys or exchanging of information. You have to open up router 1 to allow those data to come through. And here are the commands to allow you to do that. You set up an access list on this router, and if you see any data that's going in and out from this network to that network, you want to allow it, right? For the exchanging. This is just for exchanging, to allow exchanging data. If you don't do this, it's pretty much open for exchange, so anybody can come, Typically, we don't do this actually in lab. We just leave this open, and the exchange by default, there is no access list for the IP negotiation, so the negotiation is open. Anybody can negotiate a VPN with R1, really. But then they have to adhere with all the protocol setups. But it's probably a good idea to allow that. All right. So, Cisco has its own VPN protocol. This GRE, the Genetic Routing Encryption, I think it's called, if I'm not mistaken. The GRE tunnels are really just a tunnel. They take your packet, then they re-encapsulate it in another packet. No authentication, no encryption whatsoever. So you're just sending your data in a tunnel. In other words, you're taking your packet and you are re-encapsulating it with another packet, hiding it from anybody else when it's traveling across the internet. But there's no security with this at all. So this is, but it's still a VPN. All right, so let's take a look at the AIESEC policies. So if you type in and you show crypto AIESEC default policy. So this is one that's going to show you all the different types of, the priorities. 65501, here's the different priorities for this one and the default priorities. So what you want to do is let's create the first policy 1, right? And here are your choices. So you can say policy 1, I want authentication, and then you write whether, here's an example that I want you to write down, for example, right? This is for phase 1, right? So this is what you do phase 1. On router 1, you write down crypto AIESEC policy number 1 has priority number 1, and I want the hashing to be SHA, the authentication pre-shared key. I want Diffie-Hellman number 24 to exchange the key. The keys is going to have a lifetime of 3,600 minutes, and I want the payload encryption to be AES with 256-bit key, and that's it. And it's best to go to R2 and type exactly the same thing. So when the AIESEC exchange this policies, the tunnel is set. Okay? And then your second step, make sure you write that down. Okay, so those are the AIESEC key address that you want to set up, configuring the pre-shared key. So which pre-shared key you want, you write that down. So after you're done, you actually write down the key and you go and you write down the same key on the other end on R2, right? And make sure you're writing down 2.2 for this guy. I want to send the key to this guy, and R2 wants to send the key to this guy right here. Okay, so write these two down. So after we write the policy, you write the pre-shared key, configure the pre-shared key to both sides. All right, and then you actually set up the tunnel, but nothing has happened. The tunnel is not really set yet until you send interesting data, and that's what triggers the tunnel. That's what makes the tunnel. So when you type show crypto key AIESEC SA, the tunnel is not shown yet. No, there's nothing until you create an access list to trigger. What's going to trigger and open up and creates the tunnel? What's going to trigger so that the AIESEC negotiation can actually happen and sets up the tunnel is the interesting data. So you have to actually know what's going to trigger phase 1 negotiation. So you write access list and you're going to say any data that's permit IP, anything that goes from 10.01 and going to the destination 192.168.10. And this guy does the same thing, but the opposite, right? Any data that's coming from 192.168.10 network going to the 10.01 network, those are the permit access list, and then you got to apply them. All right. And now the crypto key transform set command. Once you apply those keys, that's what triggers the data. We'll see that in class. And the transform set, this is for phase 2, is when you're actually encrypting the data inside after the tunnel has been triggered by the interesting data. So crypto IPsec transform set, and here are your different types of protocols that you can use to authenticate and encrypt the payloads. All right. So you can say crypto set transform set, you give it a name, and you want an AESP, and you want the ESPH SHA HMAC for authentication. Again, you do exactly the same thing on the other side. Remember, you're writing all this down because this is an example that I want you to write down. And then you use the crypto command, the crypto map command to apply the transform set. So you type crypto map, the name of the credential set on the IPsec ISACAMP. All right, so here's the example on the crypto map configuration. And you're going to say the 101, the what's going match. So first of all, crypto map, the name, number 10, and the IPsec ISACAMP. Then you're going to say match address 101. So please make sure you take a look at the interesting data. And then once that's triggered, then the member policy one will, phase one will set up the tunnel. And then we want set the transform set R1 to R2, which means you are using the previous example that's going to set up here, this one right here. It will set and use, not this one. It will use the IPsec. I'll keep going backward. Right here, you're using ESP. EES is the encryption, and the ESP SHA HMAC. Okay, so going back in here, and then you set the peer, and you just make sure you're doing the same thing on the other side. And group 24, you got PFS, group 24, that's the Diffie-Hellman, and set the security association lifetime of 900 seconds. You do the same thing on the other side, and then you're pretty much, your VPN is set and you're good to go. You can use the command show crypto map to show your actual what's being applied. Show the interface 00 to actually take a look at the VPN if it's set or not. Okay, you can ping and make sure they can ping each other without any problems. And when you type show crypto map SA, that means the destination is, in this case, it's 172.30.2, your source is .1, and the state it's sitting idle. That means your tunnel is open and you're good to go. Your VPN is set. By the way, this only comes up if there was interesting data that triggered all of this. Okay, you can verify that the tunnel has been established by typing show crypto IPsec SA. Okay, and that's pretty much it. I know we'll go over this again in class, and we'll have a lab to do this as well. All right, so hopefully you'll have a better understanding of how we VPN works. Again, we'll do a site-to-site exercise in the lab. Until then, keep up the good work.